My name is Lakshman Purbe, and this is my lab report. The overall purpose of this lab is to study the motion of a falling object under the influence of gravity. In this lab, we will use Tracker to track the motion of a falling object, and after collecting the observed data, we will build two computational models using VPython and GlowScript. One model will only consider the effects of gravity, whereas the other one will consider the effect of the weight force and the drag force. Before progressing further, one should become cognizant of a few physics concepts. Displacement is a vector quantity that signifies the change in an object's position according to a reference point. Velocity is the vector quantity that signifies the change in displacement over time. Acceleration is the change in velocity of the object. And force is the push or pull that causes the object to change positions and have motion. In this experiment, we'll be studying the net force of an object, where the net force is the vector sum of all the constituent forces acting on this object. The gravitational force is the fundamental force that is caused by the attraction of large masses. It is directly proportional to the two masses and inversely proportional to the square of the distance between the two objects. For our purposes, however, we'll consider gravitational force to be equal to mass times gravity and mass times the constant g, which is indicated by 9.8 near the Earth's surface. Another force we'll be studying in this experiment is the drag force, which is a mechanical force generated due to the contact between a solid and a liquid. It's indicated by this formula. It is on opposing force opposes the object's motion, and it's proportional to the object's velocity. It's also known as air resistance, and for our purposes, it's equivalent to negative b times velocity squared, where b is the coefficient of drag. As seen here, the objects we'll study in a free fall usually follow this pattern, where the velocity increases in a linear manner. However, the position changes in a quadratic manner. Here is the overall setup of our experiment. In this experiment, the tennis ball is the system and the Earth is the surroundings. We initially hold the ball above the ground and place a camera at a stationary reference point to measure the changes in the ball's motion over time. We drop the ball and record its motion. One source of human error here could be the fact that oftentimes the ball can be dropped with an initial velocity. However, for our purposes, we will try to drop the ball since there is no to preserve and have an initial velocity of 0. Here is the observed data for the experiment, other than the outlier at 0.467. The data follows the norms observed in nature. In considering the computational model without the drag, we set the initial conditions of the experiment, where the mass is equal to 56 grams, the initial position is at the origin, the initial velocity is 0, time is 0, and we'll take intervals of 0.033 seconds. Obviously, the g value is 9.8, and j hat points in the positive y direction. Since we're not considering drag, b is equivalent to 0 in this case. We run a while loop that till 0.5 seconds and set the net force of the object to be equivalent to the weight force. We update the ball's velocity using the fundamental principle of momentum and Newton's second law, where ball's final velocity is the initial velocity plus the net force over the mass, which is acceleration times time. Similarly, we update the ball's position by adding it to the ball's final velocity times time to the initial position. We update the time to keep track of the time in the while loop, and we plot our model by running it and keeping track of all the position and time values. In the computational model with drag, we keep everything the same. However, we will have a b value that is not equal to 0 since we're considering drag. This b value was calculated by eyeballing it and approximating the b value to get it equivalent or close enough to the final position observed in our experiment. Similarly, another difference is the fact that our net force is equivalent to weight plus the drag force, rather than just simply being the weight force. Drag in this case is the negative b coefficient times the magnitude of the ball's velocity squared, multiplied by the unit vector that v naught, which is calculated by hat ball dot velocity. Here is the graph comparing all the three parts of our experiment. The observed values are plotted in blue dots, and the different models are plotted with a trend line. As seen here, the model actually matches the observed values. However, it tends to deviate somewhere around here and goes further down than initially predicted by the two models. As seen here, even considering the weight and drag, there isn't a significant difference between the two models, as the object in question did not succumb to the drag force as much as it should have. We believe, or I personally believe, that the deviation in the model and the observed values is caused by the fact that there was an initial velocity on the ball. The model that incorporates the effects of the drag force is the terminal velocity. The terminal velocity is predicted by the model that incorporates the effects of the drag force. As an object falls from the rest, it starts gaining speed due to acceleration caused by gravity, and as the velocity of an object increases, the drag force acting on the object also increases. At a certain point, the drag force becomes equivalent to the gravitational force, the net force becomes zero, and the object stops accelerating, and that point is called the terminal velocity. If the ball is thrown downward with an initial velocity, the terminal velocity would still be the same. The initial velocity would increase, and the drag force it would increase the drag force acting on the object. The drag force would eventually become equivalent to the gravitational force, causing the same terminal velocity. And this prediction was matched by our computational model that we built